Welcome to this explainer. Today, we're jumping right into the incredible micro to macro journey of matter. We're going to treat chemistry a lot like the ultimate set of universal Lego blocks. Seriously, if you've ever wondered how the universe scales up from completely invisible particles to the massive complex biological systems that actually keep us alive, you are definitely in the right place. Our main focus today is going to be locking down the core hierarchy of these fundamental blocks, specifically the atom, the element, the molecule, and the compound.
But hey, before we can build anything, we need to ask the most foundational question of all. What exactly is this matter that makes up everything around us? Well, the definition is actually beautifully simple. Matter is quite literally anything that has mass and takes up space. So, if it exists physically, it's matter. Period.
To answer how all this matter comes together, we're going to build up our understanding step by step. First, meet the atom. Second, elements, the chemical identity. Third, bonding, the cosmic glue. Fourth, molecules and compounds. And finally, carbon, backbone of life.
Let's kick things off with Section 1. Meet the atom, the fundamental building block. We really have to start with the absolute smallest piece of the puzzle.
An atom is the basic architectural unit of everything you can see, touch, and breathe. It literally defines matter itself. It's the fundamental building block from which all the complexity in the universe is constructed. But here's a genuinely crazy fact. Atoms are 99.99% empty space. So while we often call the atom the smallest unit of matter, it's definitely not some solid, featureless little sphere.
So what actually happens if we crack open that atom? We find three subatomic particles. Right in the very center, we have the nucleus, which holds positively charged protons and neutral neutrons. These are bound together super tightly by the strong nuclear force. Then, buzzing around the outside in different shells, we have the negatively charged electrons. These are kept in orbit by the electromagnetic force, which constantly pulls them toward those positive protons in the middle.
Moving right along to Section 2, elements, the chemical identity. Because how exactly do we get different flavors of these fundamental atomic blocks?
Think about it. Just like Lego pieces come in different shapes and colors, atoms come as different elements, like carbon, oxygen, or nitrogen. The absolutely crucial point here is that this identity is entirely determined by the atomic number, and that number is simply the count of protons packed into that atom's nucleus. Change the number of protons and you literally change the element. It is the ultimate ID badge for every single substance in the universe.
But an element's personality, meaning how it actually behaves and interacts with other elements, is controlled entirely by its outermost layer of electrons. We call this the valence shell. The inner electron shells are basically full and totally unreactive, but it's this outer valence shell that does all the heavy lifting when it comes to chemistry. Elements in the same column on the periodic table actually share chemical properties specifically because they have the exact same number of these valence electrons.
Now, what is the ultimate goal for these valence electrons? It's the number 8. Elements are always chasing maximum energy stability. For most major elements we deal with in biology, this means trying to fill that valence shell with exactly 8 electrons. You'll often hear this called the octet rule. Noble gases already have a full shell, which is exactly why they are totally unreactive. Every other element is on a constant, relentless pursuit to reach the stable state, and it's that pursuit that drives all chemical reactions.
Which brings us perfectly to Section 3, bonding, the cosmic glue. When atoms interact to achieve that stability of 8 valence electrons, they click together using chemical bonds. These connections primarily come in two major forms. First up, ionic bonds. This is where electrons are completely stolen or given away. The atom losing an electron becomes a positive cation, and the one gaining it becomes a negative anion, and then their opposite charges just pull them right together. Fun fact, this explosive stealing is exactly how a highly reactive metal and a toxic gas combine to make the completely harmless, delicious table salt you put on your fries. On the flip side, we have covalent bonds. Instead of stealing, these atoms share pairs of electrons to complete their outer shells. Covalent bonds are incredibly strong and actually form the primary backbone of biological molecules. But as you might guess, sometimes that sharing in a covalent bond isn't perfectly equal. Enter the polar covalent bond. In this scenario, a more electronegative atom basically plays tug-of-war and pulls the shared electrons closer to itself. Because electrons carry a negative charge, this unequal tugging creates a molecule with slightly positive and slightly negative ends, or poles. And this tiny inequality in electron sharing is a massive deal for us. It's exactly why water forms hydrogen bonds.
The slightly negative oxygen of one water molecule is drawn to the slightly positive hydrogen of another. This little quirk explains literal everyday miracles. It creates cohesion, keeping water liquid. It causes solid water to form a less dense lattice so ice floats in your glass. It gives water a high heat capacity to moderate our coastal climates. It allows sweat to evaporate and cool our bodies down. And it makes water an absolutely excellent solvent capable of dissolving ionic and other polar molecules.
Section 4. Molecules and compounds. Architectural structures. So what do we actually call these structures once our individual elemental blocks are finally clicked together with these bonds? Let's clarify our third and fourth major focus words.
Okay, this is a distinction that trips a lot of people up, so let's break it down. A molecule is simply any two or more atoms covalently bonded together. It doesn't even matter if they're the exact same element, like two hydrogens making H2. A compound, on the other hand, must be a combination of at least two different elements, like H2O or CO2. So all compounds made of covalent bonds are molecules, but not all molecules are compounds. It's a really precise architectural distinction that becomes incredibly important as we start to scale up.
And what's absolutely fascinating here is that you can build completely different structures using the exact same blocks. We call these isomers. They have the exact same molecular formula, but totally different layouts. We have structural isomers with different covalent arrangements, we have cis-trans isomers varying around rigid double bonds, and we have enantiomers, which are literal mirror images of each other. In biology, enantiomers are incredibly important. Because biological systems are so precisely shaped, using the wrong mirror image enantiomer can mean the difference between a highly effective life-saving drug and one that is completely inactive or even harmful.
Let's move into our final section, Section 5. Carbon, backbone of life. It's time to look at the undisputed master builder of the biological toy box.
Why exactly is carbon the ultimate foundation of organic chemistry? Well, it all comes right back to that valence shell. Carbon has 4 valence electrons. This means to reach that stable number of 8 we talked about, it can form up to 4 stable covalent bonds with other atoms. When it forms 4 single bonds, it creates a 3D tetrahedral geometry with specific angles of 109.5 degrees. It basically acts as the ultimate intersection point, allowing complex structures to branch out seamlessly in multiple directions.
This bonding versatility means carbon skeletons can grow into incredibly diverse architectures. They can vary in length, forming super short or massively long chains. They can branch off just like the branches of a tree. They can incorporate double bonds, which actually flattens the structure out into the same plane. Or they can even fold back on themselves to form closed rings.
Mapping these variations out really shows how those simple carbon changes instantly scale up. Just by varying the length, adding a few branches, or placing double bonds, you end up creating wildly complex, beautifully intricate molecular layouts. It is literally an endless combination of structural possibilities, all derived entirely from just one element's amazing geometric flexibility.
But the carbon skeleton is really just the chassis of the car. The true biological behavior, that comes from the chemical groups attached to it. By swapping out different functional groups onto these carbon backbones, we give these organic molecules very specific, life-sustaining behaviors. For instance, attaching a hydroxyl group instantly makes a molecule water-soluble. Or, crucially, attaching a phosphate group allows the creation of ATP, which is the fundamental energy-storing molecule firing within all of our cells.
Yet even in their absolute simplest form, completely devoid of complex functional groups, carbon structures are incredibly powerful. Take hydrocarbons, molecules made entirely of just carbon and hydrogen. The bonds between carbon and hydrogen are relatively nonpolar, making them hydrophobic, meaning they repel water. But way more importantly, they can pack and release massive amounts of energy upon combustion. This simple combination is exactly what forms the fat molecules storing energy in our bodies and the fossil fuels powering our engines.
So, as we wrap up this explainer, I really want you to consider a final thought. We've gone from simple protons generating atomic identity to elements interacting through covalent bonds, all the way up to creating specific molecules and complex carbon compounds. How are these invisible Lego blocks constantly clicking together and breaking apart to make you, you? Every single thing you do, see, and experience is driven by this microscopic chemistry. It is a wildly intricate architectural universe, and it's happening inside you every single second. Pretty amazing, right?